Hello, sports fans. This is Mr. Haney. I'm going to give you an update on the electromagnetic spectrum, give you some notes, and even share with you the Doppler effect. Let's get going. So, this is the electromagnetic spectrum. You can either show it this way, where the gamma rays are on the left, or the other way. So, you need to pay attention which way this visual is showing so you can understand it, because we might trick in and show it to you both ways. There are 7 different types of wavelengths that we're going to be discussing: the gamma rays, x-rays, ultraviolet, visible, infrared, microwave, and radio. Now, we won't ask you necessarily to memorize it, but you are going to have to understand how they work. The only wavelength that we can see is, of course, the visible light. And because we have it sort of flipped around, you may recognize the fact that the visible light spectrum really just contains 7 colors. And those are the colors of the rainbow: red, orange, yellow, green, blue, indigo, and violet. Red is going to be right next to the infrared part of the spectrum, where violet, predictably, will be right next to the ultraviolet part of the spectrum. As you go towards gamma rays, the frequency, how often the wavelength goes up and down, will be greater and also contain higher energy. On the far side, radio wavelength is going to have a longer wavelength, a lower frequency, less frequent, and lower amount of energy. So let's talk about that a little bit more in depth. And first of all, we'll talk about the anatomy of a wave. So this is a wavelength. Let's say that this whole white box is 1 second. The way you measure wavelength is from top to top or from bottom to bottom. The tops are called the crests. Think of a wave, an actual ocean wave cresting before it falls over. That's the top. The bottoms are called the troughs. For those of you somewhat familiar with a farm, a trough is what farm animals eat out of, a long metal tray holding all the food. So if that helps you remember, there you go. All right, so what we mean by wavelength, of course, is the distance between the 2 adjacent crests or troughs. You can measure them either way, but you must be consistent. The frequency is the number of waves passing through a point in 1 second. If you think about FM, those of you who still listen to radio, FM stands for frequency modulation, how you change the frequency. So in this case, for a high frequency wave on the top here, if we call this all a second, we have 4 wavelengths, I think is how you'd measure it. During the time that's being measured. Whereas with a low frequency wave, you just have 2. So what is the relationship between wavelength and frequency? It's rather obvious, but I'm going to state it for you. The longer the wavelength, the smaller or shorter the frequency. Okay? Longer wavelengths are not going to carry as much energy. The flip side is also true. The shorter the wavelength, the greater the frequency, and the more energy it's going to carry. So again, here's another way to look at it broken out a little bit more. Again, I will point out to you Roy G. Biv. It's squeezed right in there, and it's the only part of the EM spectrum that we can see. All right, now we have emission lines. Wavelengths of light produced by certain elements are the emission lines. That's how they show up. And this can be used to determine the composition of a star. This is why we're talking about the electromagnetic spectrum. Now, to give you an example, if you're a scientist and you're looking at stars and studying them, the emission spectrum for hydrogen, which all stars will have hydrogen, will look like this. That's different for helium. You can see the lines are somewhat different. And then you start moving down the periodic table. Here's calcium. And then we have sodium, iron, magnesium, and so on. All the elements are going to give off different emission lines. Scientists use spectroscopes to view stars and record observations. So this is very similar to the spectroscopes we have at school. You can look at emission lines through this. Now, obviously, it's not as complicated or as expensive as what scientists have, but it's still useful. They can tell what elements the stars are burning by looking at the emission lines. Furthermore, if the star is moving away from Earth, the light given off by the star will favor the red part of the spectrum. Okay, this is known as redshift, and it tells us the star is moving away. However, if the star is moving towards the Earth, the light given off favors the blue part of the visible light spectrum, and this is known as blue shift. So we have a diagram here showing you this. This gentleman here is viewing star moving away, so it's the light is favoring the red part of the spectrum, when we call that redshifted. And this gentleman here is watching a star moving right towards him. Look out, sir. And because it's moving towards him, we have it as blue shifted. And that sort of moves us to the Doppler effect. I think we've all experienced the Doppler effect one way or another. I know sometimes you see a plane before you hear it because that sound is moving in a different direction. The Doppler effect can increase or decrease in the frequency of sound or light or other waves as the source and observer move toward or away from each other. So this video will explain it pretty quickly.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look at your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right, so that's the Doppler effect. We'll show how it works audibly one more time. If you're hearing a police car coming your way and they have their siren on, depending upon where you are in proximity to the car, you'll have a different sound. For example, here is something, I believe this is from Europe with emergency vehicle. Sounds a little different as it approaches and then as the fire engine goes away. Blurry, but it serves a purpose. Now, I will put this next video, attach it with the assignment. If some of what I've said doesn't make sense, maybe this Brit on this next video can help you better understand the electromagnetic spectrum. Thank you for listening and have a great day.